Okay, so today it says we're going over confidence intervals for the mean, but before that I was just going to mention as of midnight tonight, Sakai will stop accepting submissions for homework 1. You can still email them to me, but we are planning to grade them early next week, and I mean, I understand stuff happens in life. If there are extenuating circumstances you can't get it done by today, I will be reasonable, but please do email me. I'm just trying to avoid like a couple years ago where everybody was turning in their homeworks like a month late, and we had like 2 homeworks graded by the end of the semester. So, yeah. But as you'll recall, on Wednesday we discussed if you know the mean and standard deviation of a normal distribution, you can compute probabilities involving the distribution of the sample mean. In practice, though, we're not going to know the population mean and standard deviation. If we did, there would be no reason to make inferences about the mean in the first place. So today we're going to discuss how you can use the sample mean and sample standard deviation to make inferences about the unknown population mean and standard deviation. Oh, recall the definition of statistical inference. The idea is you're using sample data to draw conclusions about a population. That on Wednesday we discussed the scenario that given a population mean, we try to make inferences about the sample mean, or in other words, given a population parameter, we're trying to make inferences about a sample statistic. In real life, what you want to do is, given a statistic based on a population, draw inferences about a population mean mu. That, say, you want to see how gene expression changes in certain tumor types, and you want to try to make inferences about all patients with that particular type of cancer. You collect a set of patients with that cancer, measure the gene expression levels for the genes in that tumor, compare them to healthy people, then use these sample means to draw inferences about this larger population that we do not observe. Well, I'm going to briefly outline how you do this using the normal distribution theory that we've discussed previously. Don't worry too much about the math. You're not going to have to do these details. It's just felt like it's something that I should at least discuss. We showed in previous lectures that if your sample size is sufficiently large, the sample mean x bar will be approximately normally distributed, with mean equal to the population mean mu and standard deviation equal to the population standard deviation sigma divided by the square root of the sample size n. And likewise, if you take x bar minus the mean divided by sigma over the square root of n, that should be normal with mean 0 and standard deviation 1. But to find a 95% confidence interval for the population mean mu, we can use this equation that I just listed here, and I'll show you the steps on the next slide. So, the first thing that we have to do is find the approximate quantiles of the normal distribution with mean 0 and standard deviation 1. You can use this in R or just look it up. It turns out that the 2.5% quantile and the 97.5% quantile of the normal distribution with mean 0 and standard deviation 1 is almost exactly 1.96. Oh, yeah, there's the R command to do it. As we've discussed before, you can use qnorm 0.975. It's almost exactly 1.96. Or if you do qnorm 0.025, you'll get minus 1.96. So, using the equation from a couple slides back, we know that the probability that this quantity x bar minus mu divided by sigma over root n, the probability that's between minus 1.96 and plus 1.96 is equal to 0.95. So if we do some algebra, that implies that, I'll just skip down to the punchline at the bottom, that if we look at the sample mean x bar minus 1.96 times sigma over square root of n, and x bar plus 1.96 times sigma over square root of n, there's a 95% probability that this interval will be chosen such that it contains mu. So in other words, we can make inferences about mu using x bar, which is a really nice property. Taking this to like a real world, let's take this cancer example again, that you calculate the mean expression level of a particular gene among some sample of cancer patients. Then you can take, if you take that mean minus 1.96 times sigma over root n and the mean plus 1.96 over root of n, then the 95% of the time when you do this, that interval will contain the true population mean mu. So in other words, even though this true population mean is unobserved, we can still find a confidence interval for that unobserved mean. And one note about the way these confidence intervals are calculated. In a perfect world, this interval x bar plus or minus 1.96 sigma over the square root of n would be a 95% confidence interval for the mean. Now, in practice, that doesn't work because it requires us to know the population standard deviation sigma, which we're never going to know. I mean, there's pretty much never going to be a situation in practice where you don't know the population mean, but you do know the population standard deviation. Luckily, there's an easy way to work around this issue. If you go through some funky math that I won't torture you with, it turns out that if rather than using the quantiles of the normal distribution, i.e. 1.96, you can replace the 97.5% quantile of the normal distribution with the 97.5% quantile of another distribution called the t-distribution, and take the sample mean plus or minus that quantile times the sample standard deviation s divided by the square root of n. And that works much better because in general we won't know sigma. That's a population parameter that we can't observe, but s is just the sample standard deviation based on your data that's easy to calculate. So if we just simply replace the quantile of the normal distribution with the quantile of the t-distribution, then we can calculate confidence intervals for the mean without needing to know the standard deviation of the overall population. And just a quick note on the t-distribution. It's another bell-shaped distribution that looks a lot like the normal distribution, but it has slightly thicker tails. The intuition behind this is that we don't know the standard deviation of the distribution exactly. We have to estimate it. And since we have to estimate it, there's a certain amount of uncertainty in that estimate. And because of that uncertainty, we have to make our confidence interval slightly wider to adjust for the fact that we had to estimate the sample standard deviation. Oh, this graph here shows the t-distribution for various degrees of freedom. I don't know if I explained degrees of freedom on this previous slide. Note this notation here, I say x bar plus or minus t sub n minus 1, where t sub n minus 1 is 97.5% quantile of a t-distribution with n minus 1 degrees of freedom, and is once again the sample size. So the larger your sample size, the more degrees of freedom this t-distribution will have. This idea of degrees of freedom is a complicated thing that I really don't want to torture you with that, but for the time being, suffice it to say that it's just one less than your sample size, and it's a number that you will plug into R so that you get a confidence interval of the appropriate width. This slide, you can see the pink line is the t-distribution with 1 degree of freedom, and you can see it's much less concentrated at the center of the distribution. The tails are much thicker, that you're much more likely to observe extreme values, either extremely small values or extremely large values on a t-distribution with 1 degree of freedom than you would with the normal distribution. As the degrees of freedom of the t-distribution gets larger, it gets closer and closer to the normal distribution. As you can see here, more and more of the distribution gets concentrated towards the center, and the tails get narrower and narrower. And as the degrees of freedom of a t-distribution goes to infinity in this graph, it becomes the same thing as the normal distribution, that a t-distribution with infinite degrees of freedom actually is a normal distribution you can show. And as this graph implies, even for relatively small numbers of degrees of freedom, the t-distribution becomes almost identical to the normal distribution. But it's better to use the t-distribution anyway, just because it's better to have your confidence interval slightly too wide than too narrow. And a note on interpreting confidence intervals. I mean, this isn't something that I'm going to harp and scream about too much, but I mention it mainly because, like, if you have any experience with submitting papers to journals, there's always one smart aleck reviewer that if you make some tiny mistake like this, they assume that you're an idiot and try to kill the rest of your paper. So I'm bringing this up just so that you know not to make this mistake. If you say there's a 95% probability that your confidence interval contains the true value of the mean, strictly speaking, that's not a correct statement. The reason why is because the population mean is some fixed number. We don't know what it is, but it's some number. In other words, either the confidence interval contains the mean or it doesn't. So strictly speaking, the probability is either 0 or 1. It's not 0.95. And I mean, super nitpicky point, but you will find people in this world that if you say there's a 95% probability that the confidence interval contains the mean, that they will go completely ballistic on you and get really angry. So to avoid those people, it's better to say something like there's a 95% probability that the confidence interval we calculate will contain the true value of the mean, or 95% confident that the confidence interval contains the true value of the mean. Because the actual interpretation is more along the lines that if you calculated confidence intervals for the mean using 20 different samples, then 95% of the time, then 95% of these intervals will contain the true mean. That doesn't imply that that's true for any one interval. For any one interval, the probability is always 0 or 1. So I've got some graphs here to sort of try to illustrate what's going on here. This is just some simulated data that basically I generated some random data with mean 50, standard deviation 10, and a sample of size 10. In each case, I calculated a 95% confidence interval. And for each of these lines, the top of the line is the upper confidence limit, and the bottom of the line is the lower confidence limit. And I did this 50 times, and you can see there were a couple, that one right there, and where's the other one? I don't even see it. Well, I can't see. Yeah, I guess that one over there also just barely missed. So there were out of 50 confidence intervals, 2 of them did not contain the true value of the mean. And if we do 95% confidence intervals, then 95% of them should contain the mean, 5% or 1 out of 20 shouldn't. Well, the fact that we see 2 that didn't contain the true value of the mean is almost exactly what we expect. And you'll notice here that the 2 that don't contain the true value of the mean, they just barely missed. So the vast majority of the time, if you get unlucky and your 95% confidence interval doesn't contain the true value of the mean, it won't miss by very much. And then I redid this little simple simulation study, increasing the sample size from 10 to 25. You'll notice that compared to the previous slide, the confidence intervals got much narrower, but this time we had a total of 4 intervals that didn't contain the true mean. Those 2 right there, 1 over there, and 1 other that I'm not immediately seeing, but no, I guess 1 further to the left. Again, they don't miss by very much. In this case, we got a little unlucky. Normally, we would expect only about 2 or 3 of these confidence intervals to not contain the mean. This time we had 4. But this just kind of illustrates the point that when you increase your sample size, your confidence interval will get narrower, but you don't increase the probability that you actually contain the true mean. That stays at 95%. If we want to be more certain that we captured the true mean, you can make your confidence intervals wider and do like 99% confidence intervals rather than 95. But you can't increase the likelihood of your confidence interval containing the true mean just by increasing your sample size. If we wanted to be more certain that we contain the true mean, this shows the same example from the previous slide where I do 99% confidence intervals rather than 95, and you can see compared to the previous slide, the confidence intervals are wider, but the probability of a given interval doesn't contain the true mean goes down. In this case, there's only 1 that doesn't contain the true mean, and it just barely misses. So if it's important to be absolutely certain that your confidence interval contains the true mean, you can make your confidence interval wider. Although in practice, I'm not sure I've seen a single published scientific paper in my entire life that ever reported a confidence interval that wasn't a 95% confidence interval. So, yeah, just mentioning that. So, to give like a real-world bench science example of when you might want to use this procedure, this was a data set that was given to me by a student named Valerie Soldato who was in this class a couple years ago, and she was measuring urea secreted by 27 liver cell samples. As an aside, if anyone else ever has data that they want me to use for examples in this class, or would let me use for examples in this class, get in touch with me, because I try to make the examples in this class as relevant as possible, but finding good examples is actually surprisingly hard to do. But that aside, so she wanted to know the average urea secreted by her liver cell samples and a 95% confidence interval for the average urea secreted. And I was going to put this data set on Sakai if anybody wanted to try it, but I forgot. I'll do that when I get back to my office. But if you'll recall from the formula a few slides back that defined an lower and upper 95% confidence interval for a data set with sample size 27, you would take the sample mean minus a the 97.5% quantile of a t-distribution with 26 degrees of freedom times sample standard deviation over the square root of 27. The upper bound would be the same thing with a plus instead of a minus. So I first read the data set into R using the read.csv command. This data set just contains a single column called urea. So if I want to compute this confidence interval directly, the way you can do this in R is I just say mean urea, that's x bar from the previous slide, just the sample mean, minus this function qt, that stands for quantile of a t-distribution. It takes this is a new function, and it takes two arguments. The first, it's really similar to q norm. The first number that it takes is the value of the quantile that you want. In this case, it's the 97.5% quantile. And the second parameter is the number of degrees of freedom, which is 26 in this case. So if we say mean urea minus the appropriate quantile of the t-distribution times the standard deviation of urea divided by the square root of 27, that gives us the lower 95% confidence bound, which is about 33.2. To get the upper 95% confidence bound, we do the same thing, only we go plus the quantile times the standard error, and we get about 37.05 for the upper 95% confidence bound. And as I said before, the qt function gives us the pth quantile of a t-distribution with specified degrees of freedom. In particular, if we say like qt 0.975, 26, it gives you the 97.5th quantile of the t-distribution with 26 degrees of freedom. Luckily, you don't have to mess with that annoying formula every time you want to calculate a confidence interval in R. There's a simpler and faster way to do it using this function t.test. As the name implies, this function is primarily used for hypothesis testing rather than calculating confidence intervals, but you can also use it to calculate confidence intervals. We'll discuss some of the other uses of this function in the future, but if you say t.test urea, you can see it gives a 95% confidence interval, 33.2 to about 37.05. Exactly what we got using the formula on the previous slide. The advantage to this is you don't have to remember the formula. You can just use this single one-line command and it will automatically give you the confidence interval. And this t.test command is highly versatile. We'll be using it for a number of different things over the next few lectures. I'm not going to list all the commands here. If you're really curious, you can look at the help file or just stay tuned for the next couple lectures. But for the time being, if you use the really simple version of this command, just say t.test of x, that will give you a 95% confidence interval for the mean of the vector x. And if, for whatever reason, you wanted a 99% confidence interval to be absolutely certain that or at least be more certain that your confidence interval contains the true value of the mean, you can pass this parameter conf.level to t.test. Say, rather than a 95% confidence interval, I want a 99% confidence interval, and you can see it ends up being slightly wider. It goes from about 32.5 to 37.7. In real life, you will do this very rarely, if ever. Every single published paper I've seen in my entire life always reports 95% confidence intervals. It was R.A. Fisher, who was kind of the father of modern statistics, at one point said that 95% is a good confidence level to use, and it has become gospel in the field ever since then. Kind of weird the way that science works that way, but in all the homeworks, I'm pretty sure I will ask you to do 95%, and in real life, that's probably always what you will use as well. And in general, I mean, when I calculate these confidence intervals, when I'm doing this in my day-to-day work, I always use t.test. It's quicker, it's easier, you're less likely to make mistakes, it's superior in just about every way. Pretty much the only reason why you might want to use that formula instead of t.test is to use t.test, you have to have the full data set in R. If you don't have the full data set, if all you have is the mean and standard deviation, you can't use t.test. In that case, you will have to use the formula directly. That's not common, but it does happen on occasion. The most common scenario is, say you're reading a paper or something like that. They don't give you the data from the paper, but they report a mean and a standard error in their paper. Given the mean and the standard error, you could calculate a 95% confidence interval for the data in the paper. Using that formula, you wouldn't be able to do it using t.test. But that's probably the only scenario where you would want to use this formula. And for the purposes of this class, there might be like one homework problem where I ask you to do this without using t.test, but it's not something I'm going to ask you to do on a regular basis. So, now some discussions about validity of confidence intervals and as I've said before, this may be the most important part of today's discussion, because the way I see it, it's, as I've said before in this class, I mean, I don't really care if you remember how to calculate a confidence interval or do a t-test 2 years from now. If you forget, it's easy enough to look it up, or just send an email to your statistician friend saying, help me calculate this confidence interval. On the other hand, if you use a confidence interval in a situation where you shouldn't be using it, or the assumptions for your confidence interval aren't satisfied, then you end up publishing garbage results, and that's the biggest thing to avoid. So, if there's any part of today's discussion to pay attention to, it's this part. That it's easy to calculate confidence intervals, it's also easy to mess them up. It's a lot of times you'll see, even in published papers, people will just stick their data into R, their favorite statistical program. It'll spit numbers back out. They'll go punch those numbers into a table and run and publish their paper. That doesn't mean that the analysis was valid or that the numbers they stuck in their table are going to be accurate. It just means the whole garbage in, garbage out principle. So the most important thing to take home from today's discussion is when it's okay to use a confidence interval and what things can go wrong that would make your confidence intervals be invalid. So, one example is, this was out of a textbook that I stuck in the lecture slide because it made me smile, and apparently this was an actual published study, that they found 10 people who used marijuana heavily who had an average IQ of almost 130 versus a population average of 100. That is much larger than the mean of the general population. And they were members of a religious group that used marijuana for medical purposes. Now, can we safely conclude for this that we should all go get high on pot and it will make us smarter? Well, not exactly. Obviously, this is not a random sample from the overall population of marijuana users. These people who use it for religious reasons are probably not representative for various reasons. And the formula for the confidence interval considers only sampling error. It doesn't take a biased sample into account. If your sample's biased, if you don't consider confounding variables, it does not matter how large your sample is, what statistical method that you used, you're dead in the water straight out of the gate. If you'll recall from early in the course, the infamous Literary Digest poll in 1936 that surveyed over 1 million people and predicted that Alf Landon would easily defeat FDR in the presidential election. It was a biased sample. They had too many rich, white, affluent people in their sample. If your sample isn't representative of the population, your confidence intervals are completely meaningless, and the fact that you reported a confidence interval doesn't make it any more likely that your results are actually true. Another place that you can get into trouble is that all of these formulas assume that the observations are independent of one another. If the observations aren't independent and you just try to mindlessly plug these numbers into the formula, you'll get the wrong answers. To give an example of this, in a study that I worked on in my center, we collected the systolic blood pressures for 84 patients in the study, and we measured the systolic blood pressure twice, just in case maybe they were nervous the first time we took it or whatever the case may be, and we wanted to find a 95% confidence interval for the true blood pressure. I think I was going to put this data on Sakai as well, but forgot. So try to do that when I get back to the office as well. So there are a couple issues with trying to draw inferences about the blood pressure of the general population based on this particular sample. The first potential issue is that patients in a clinic generally are not representative of the population as a whole. In general, anytime you use a clinical sample to collect your data, the people tend to be more affluent, more educated, more white, more female, and older than the overall population. So the sample that you get in a clinic is almost certainly not going to be representative of the general population. But aside from that macro concern, in terms of just using a formula, you have to be careful when you choose the degrees of freedom here. That when my collaborator first tried to analyze this data set, what he tried to do is he just took the 168, 84 times 2 blood pressure measurements, stuck them all into the program, and just computed a confidence interval that way. In R, you read in the blood pressure data, it contains 2 columns called systolic BP1 and systolic BP2. What he wanted to do is just merge those 2 columns together so you had 164 total data points and calculate the confidence interval for that. That is actually incorrect because these observations are not independent of one another. The vast majority of the time, systolic BP2 is going to be almost exactly the same as systolic BP1 for a given person, so they contain a lot less information than if we had simply collected a sample from 164 or 168 different people. So, I guess 162 different people, I should say. But, so, as I said, we measure blood pressure twice for each subject. They're not independent, they're very strongly dependent. So a better way to do this is to just average the two blood pressure measurements for each patient and then take the 95% confidence interval for this average. So how would you do that in R? Well, R is smart about this sort of thing, that if you give it two vectors of numbers and say add it together, divide by 2, it's smart enough to do it element by element in the vector. So if you do a command like this, systolic BP1 plus systolic BP2 divided by 2, it takes the first pair of measurements, adds them together, divides by 2, takes the second pair of measurements, adds them together, divides by 2, does this for all of the 81 samples in the data set. You end up with this systolic BP average vector, which is a vector of length 81, where each element of the vector is the mean of the two measurements from each person. So if we see here, we get a confidence interval that goes from about 123.3 to 130.9, which, if you compare it to what we got when it was done incorrectly, I mean, it's not drastically different, but you can see this confidence interval is a little bit too narrow. It goes from 124.3 to 129.9. Not horribly off, but it's a little narrower than it should be. If you don't average the two measurements, you end up with a confidence interval that's too narrow. If one simple way to deal with this issue is to just average dependent measurements that average the two blood pressure measurements. In this case, that probably solves the problem just fine. It gets a little hairier if you have large numbers of repeated measurements. Say you have like 60 mice, each of which comes from one of 10 litters, so you'd have to average across 6 mice in each litter. If you could do that and it will give you valid confidence intervals, but you end up throwing away a lot of data that way. There's some more sophisticated methods that you can use to handle that type of data. And if we have time later in this course, I'll give you a brief introduction to that. And if you frequently deal with data like that in your lab and would be interested in knowing how to do that, send me an email and I'll make sure to cover it later in this course. But if you get even more funky dependence patterns where you have like time ordered data or something like that, then send me an email or send an email to your favorite statistician, because that's a really complicated scenario that I'm definitely not going to touch in this class. And the other thing that can mess you up when you try to compute these confidence intervals is if your data is non-normal. The t-test assumes that your data is normally distributed. Luckily, the vast majority of the time you won't get into trouble if your data is non-normal. As I said before, the central limit theorem will make it so that these formulas work, even if your data is non-normal. That if your data set is reasonably well behaved, 20 to 30 observations, you should be fine. If your data is really badly skewed with lots of outliers, you might need more like 70 or 80. In practice, very rarely do people even bother to test this assumption of normality. They just run the t-test and assume everything's fine, and the vast majority of the time it is fine. However, if you try to apply the t-test to a small sample, particularly a small sample with lots of outliers or something, you can get into problems. In fact, there will be one homework assignment later in this course where I give you a data set that has a really bad outlier and a relatively small sample size where if you just mindlessly apply the t-test, you'll get incorrect results. So, how do you test to see if your data is actually normal? For the t-test, this isn't really essential to do, but I decided I would describe it briefly just because when I taught this earlier, I got questions about it. And later on in this course, there are situations where it's more important to test that your data is normally distributed. And so I figured I'd spend the last 5 minutes describing how you do that. The easiest way to test for normality is to do what's called a normal quantile plot, or more commonly a normal QQ plot. And the way that you do that is you plot the quantiles of your data against the quantiles of the normal distribution. If the data is normal, this should be a straight line. If the data is non-normal, then you'll see departures from the straight line. And the way that you do that in R is you can use these commands QQ-norm and QQ-line. This is, say, if you'll recall the Michelson-Morley data from a few lectures ago, say we wanted to know if that data is normally distributed. You can just go QQ-norm data, give it a header, and then if you want to see the line that the data should fall on, if it's truly normally distributed, you can use this command QQ-line. So, yeah, QQ-norm gives you a normal QQ plot, and QQ-line gives you the line the data would follow if it were perfectly normal. You don't really need to do that, but it helps the graph. It makes the graph easier to read. So for the Michelson-Morley data, it looks like this. And for the most part, this is pretty good. I mean, you see a couple outliers that are larger than you would expect to observe under the normal distribution. You see it goes a little bit above the line there and a little bit below the line there. That's an indication that the tails of the distribution are a little bit heavier than they would be if the data were really normally distributed. But it's not that bad. If you have a data set that looks like this, I mean, I would use a t-test without batting an eye. Because here's a histogram of the Michelson-Morley data. As you can see, it's pretty bell-shaped. Couple outlying observations, but yeah, you're definitely fine applying a t-test in this case. Now the Loblolly-Pine data that we used a few lectures ago, as you'll recall, that was not particularly normally distributed. I mean, you don't see outliers and stuff, but it's certainly not bell-shaped by any means. So you plot the normal QQ plot there, and you can definitely see it is not normally distributed. The tails are much heavier than you would expect to observe under a normal distribution. But even in this case, we did the numerical experiments and showed that the central limit theorem seems to work just fine. Generally, something like this isn't that big of a deal. It's outliers and skewness that really kill you in terms of getting into trouble with normality assumptions being violated. So even the Loblolly-Pine data, this isn't normal, but it's a sample of size 80. Usually by the time you have a sample of size 80, it doesn't matter how bad your data is going to be, and this data really is not that bad. Just to give you a case where it looks really ugly, this is some data on rock permeability that's also built into R. You can see the vast majority of rocks are not very permeable, but there's a small number that have significantly higher permeability. This would be an extremely skewed data set that, well, I'll show you the QQ normal plot here. As you can see, not anywhere close to being on a straight line. Even in this case, for a sample this large, you're probably okay if you use a t-test. But if you use some other methods that depend more strongly on the assumption of normality, you could get into trouble if you assume the data was normal, because it quite clearly isn't in this case. So, things to remember today: you can compute confidence intervals for the mean using the t-distribution. For the confidence interval to be valid, you need to have a random sample from the population of interest, and they need to be independent of one another. And if your sample size is small, then your data needs to be normally distributed. And if you want to test if a population is normally distributed, you can use these normal QQ plots. And here's the R commands that are new today. Qt gives you quantiles the t-distribution. T.test gives you 95% confidence intervals for a vector x. And if you want to assess normality, you can use QQ-norm and QQ-line. Any questions about any of this? Okay. Discussion section today at 3:30. If anybody needs help with R or has questions on the homework or about the class generally, and also please turn in homework 1 if you haven't already.